from Ashwin, and then we'll have the networking event. Just to let people know, this is a recorded event, and Jill will be handling that. Thank you, Jill. So a brief introduction to the data science team, the study team. I'm Mide, a petroleum and geoscience engineering PhD aspirant at UT Austin. I'm in charge of operations. We've got Anab and Christopher on the call. They're in charge of marketing and programming roles. Anab, Christopher, you guys could drop in and just say hello so you can be identified with.
Sure, thank you. Hello, everyone. My name is Christopher Lamy. I'm one of the team members here, and I hope you all have a great session ahead.
Okay, Arnab.
Hi, everyone. My name is Arnab, and I'm one of the team members here, and I'm currently a PhD student at UT Austin, and hopefully this session will be useful for all of you.
Okay. So as Arnab is rightfully introduced as a PhD student at UT Austin in geophysics, Christopher worked with Ali Burton 2012 to 2020, and right now he's a PhD candidate at Colorado School of Mines. Charles is on here, but he can't make the meeting today. However, he's in charge of integrating our combined efforts and contributions. Our roles and background may differ somewhat, but at the end of the day, we're bilingual. We all speak data and energy. You could use the email in the description here to get across to us, to contact us when able. We are open to collaborations, suggestions, and feedback. So the speaker of today is someone who I've had the opportunity to work with as a student when I was at OU getting my master's, and an intern last summer at Reservoir, Ashwin Venkatraman. He's the CEO and founder of Reservoir, a company that prefers intelligent solutions using data analytics and machine learning algorithms to solve various reservoir engineering problems. He has a unique mix. He's worked in academia and the industry. Ashwin worked in Shell for over 12 years in India, Netherlands, Houston, in various roles, project management, reservoir engineering, and technology deployment. So I could say we're expecting him to give a full punch, presentation. Before we proceed, all questions for Ashwin are to be asked in chat. I would relay this to Ashwin during the question and answer sessions. On that note, over to you, Ashwin, for your presentation.
Thanks, Adimade, for the warm introduction. I appreciate. It looks like the committee has come a long way from our earlier days. I remember having early conversations with Charles Cosa around, why can't we at Austin have our own DSEA group? So it's great to see things taking shape, and delighted to be the first speaker. And what I'm going to do is just pull up the presentation. All right. So are you able to see my screen? All okay on that front?
Oh, yes, we can see your screen, Ashwin.
Excellent. So, without further ado, what I want to start with is, some motivation around reservoir engineering workflows, why we care about what we do. Of course, I will touch upon some background of models. We all know a little bits and pieces of different models. I just want to make sure that, all of us have some common understanding, at least as we see it at Reservoir. And of course, I shall touch upon case studies, talking about some successful implementations. And I shall broadly go over how combination of different models is actually what is the need of the hour, whether it is for production optimization for water floods. If it's field development planning, it doesn't matter whether it's conventional, unconventional, the traditional field development planning that we often do as part of reservoir engineering, or even touch upon the idea of bottom hole pressure prediction, especially in cases where your pressure gauges have failed, especially in subsea. And finally, draw on some conclusions on how we are at the cusp of a lot of these new age modeling tools, which can really help us automate decision making as it pertains to greenfield or brownfield, depending on which field you're looking at. And one central point that I would like to drive through the course of this talk is how the whole idea of hybrid models are formed, and how they can really be our ally, especially when it comes to trying to overcome the individual limitations associated with each of those models. All right, so let's take a step back, and for those of us who've been around long enough, do you remember how perhaps a person like Bob would be planning vacation in the 1980s? I understand we have a mix of folks here. So for those of you who are old enough, let's say that Bob is trying to take a vacation to New York City from Austin, right? These are the steps that he would typically do back then. He would start with the yellow pages, search for hotels in NYC, narrow down to a zip code, possibly start calling each hotel, check for availability, perhaps, evaluate the best alternative amongst those that are available. And in certain sense, continue this process until he ends up reserving a specific room for himself. Now, it's quite surprising that when you talk about Bob trying to run a reservoir simulation today, which is primarily the decision-making tool in our oil and gas industry, there are actually a lot of parallels with those steps. So you start with learning the manual. There are umpteen keywords and framework that one needs to figure out. Perhaps by that time, you're already lost. You probably have to also select an appropriate physical model. Are you talking about a black oil simulation, or are you talking about a compositional simulation? Is it a gas condensate reservoir that you're trying to model? And then, of course, you go into nitty-gritties of providing input parameters. So essentially, what viscosities do I use? What densities do I use? Do I have the fluid PVT reports that I need to incorporate, right? And then, you struggle, you probably put it together, you end up running it. But then obviously, you never get it in the first step, right? So, maybe it runs, maybe it doesn't. And you have to go back and forth to try and actually, get some success. And again, this is just trying to set it up, right? And the whole part around analysis, as well as trying to determine a decision around it, comes through, which is obviously the most important step. But one finds oneself being exhausted in just trying to set things up. So this was, I was Bob running reservoir simulations not too far back when I was with Shell, and so that was really the inspiration behind starting Resermine. The whole idea that we definitely needed much better decision-making tools, which primarily can help us guide decisions. Now, that's not to say that there haven't been other tools, but somehow, I'm just trying to summarize how a list of different models that are typically available when it comes to reservoir surveillance and management models. And I've also listed some of these challenges associated with each of these different models. So when you talk about analytics, what you're really looking at is, some kind of a statistical method, some cross correlations perhaps, or perhaps, trying to derive some relationships where you're trying to run them only on the data. So on the data that you observe, it could be the temperature data, the pressure data. And there, of course, the challenge is to identify which data set to run these relationships on. You can talk about machine learning models. And this is, of course, something that we are embracing in our industry. These typically use the supervised learning. So I shall focus more on supervised learning, perhaps touch upon random forest and neural network, where you find a lot more successful applications around. So these are new methods, and I would want to believe that we as a community are still learning how to integrate it with existing workflows. And hopefully I'll present a couple of examples of how some of these can be incorporated. There are these other category of models called reduced physics or reduced order models. Now, they've been around even before we started embracing simulation in a big way. So these were, let's try to describe perhaps the first order physics using simplistic equation. So you might have some governing background equations that you're trying to describe. And the good thing about these equations would be that perhaps they are ordinary differential equation, which means you have a neat and simplified analytical solution. So they've been around for a long time. And of course, these are accepted academic techniques. People understand that they indeed kind of help you embrace or capture a lot of these first order physics. But then there are some challenges when it really comes to applying it to field data. So think of them existing as Excel sheets, and suddenly you're trying to apply it to a field which has over 500, 600 wells, which really blows up the nonlinear optimization problems that you're looking at. Excel sheets wouldn't even open with such large number of wells. And of course, there are reservoir simulations which we've been looking at. We've all get trained in as part of any course. So these are physics-based model which is trying to simulate flow, right? So I don't need to go over that. So there are these categories of different models. And what I wanted to emphasize was when I talk about hybrid models, what I really mean is trying to combine a couple of these techniques together. So it could be, maybe machine learning coupled with reduced physics, or it could be reduced physics coupled with reservoir simulation. And through that combination, perhaps combining it with machine learning. So I shall go over some of these combinations and how they really help not just overcome barriers or limitations associated with each of these individual approaches, but also help in really driving and impacting a lot of surveillance and management that we do often in operations. And the whole idea behind Reservoir Engineering Expertise in a box is to go back and have these hybrid models run in the backend so that you can go from data all the way to decisions in a matter of a few clicks, if you will. All right, so let me touch upon some of these individual models, at least in the context of some examples and cases that I shall be talking about. This is in no way an exhaustive set. I just want to touch upon some of these modeling tools in the context of the case studies that we'll discuss later. So the first one that I want to talk about is these analytic-based approaches. Obviously the one that comes to mind is the cross-correlation analysis. Inspired by signal processing, where what you're really trying to do is determine how perhaps two different time series data are related to each other. So let's say XT and YT. XT is your injection injector well data, so injection rates measured as a function of time, right? YT is the production data, so production rates mentioned as a function of time. So you can determine what are referred to as Pearson's correlation coefficients between just these two data sets, right? So what you do is you can introduce a phase lag, which is a tau. So what it really means is you are perhaps comparing, let's say, the first 10 months of injector I1 data with, let's say, the first 10 months of producer P1 data, right? In that case, the tau is 0. So when you introduce a phase lag of 1, what it means is you're comparing the first 10 months of I1 data with month 2 to month 11 of production data. So you're just sliding the time scale there. And so you can run these computations, you can evaluate these correlation coefficients. So the idea is if one injector and one producer are strongly related, they are reflected in a high Pearson's correlation coefficient. And the tau at which that occurs, the phase lag at which that occurs is reflective of whether it's an effective or ineffective injector. What I mean by that is if I make any change in my injector, if that's immediately translated onto the producer, I will get a stronger Pearson's correlation at a lower phase lag, right? And similarly, if I get a strong Pearson's correlation at a much higher phase lag, what it means is that the injector and producer pair are related, but they are related at a much later time frame, meaning that you are getting that sweep occurring in your reservoir. So just wanted to illustrate how this simple concept translates into qualitatively identifying which injectors and producer pairs are related. Of course, these were introduced back in the 1990s, and we also have some publications in this area on how one can qualitatively use it to really determine which specific injector producer pairs are related. Now, in addition to Pearson's correlation coefficient, you can also use the Spearman's rank correlation coefficient, which kind of ranks the data rather than using the actual data. So in certain sense, this analysis can really help you identify thief zones in your reservoir, as well as identify which are your effective injector producer pairs. So you can start seeing the impact, especially when you're operating 500, 600 wells. Even knowing which 10 to 20 pairs to concentrate on is a big deal for the operations. All right, the other approach that I want to talk about is, of course, the machine learning. So there are decision tree algorithms. I'm sure a lot of you have come across them. So the idea there is you're asking a series of questions and hence classifying the information. So it's a widely used method. I want to focus on random forest because that's some of the things that we've observed perform really well. They're widely used model, used for classification as well as for regression problems. And essentially, you're just asking, as I mentioned, a series of if-else questions that can lead to decisions. And then you can start weighing, perhaps asking around, which of these questions and, identify feature importance based on that. So the central idea being that you can rank, how some of these questions are critical in the overall classification or regression problem that you're trying to solve. All right. The other kind of model that I touched upon at the beginning, reduced physics model, and one particular model that we found particular fancy towards is something called the capacitance resistance model. So they were introduced back in the 1940s, and as you can see, the central idea behind these models is, let's say that you have a producer, a QJ, and several of these injectors here. So I'm just trying to illustrate a case. Of course, there are multiple producers, perhaps in the entire field. So let's just assume that there are just 6 injectors, and we are looking at one specific producer out of multiple producers that there are. So here, the central idea is that every injector and producer pair is actually related by a fraction called Fij, or the gain values. And so essentially that is reflective of perhaps, how much of percentage of whatever you're injecting really reaches or contributes to production coming in from that specific producer. So when you cast those equations in a simple mass balance format, what you get is like an analytical solution for that. And you can actually go back and analyze what each of these terms are. So the first term, of course, something we are all aware, if you wouldn't inject anything, how typically all wells would decline, right? So that's the natural decline. The second is the impact of injection. So, you have the Fij into I, Fij being the contribution of injector I over a specific producer J. And of course, the third term, which represents the variation in the bottom hole pressure. Now, these have been widely used, especially to try to optimize specific field cases. And the idea here is how much you're producing. So QJ is known, right? How much you're injecting. So you can go back and try to have this as a nonlinear optimization problem where you can go back and identify what those Fijs are. Yeah, and these Fijs are typically values between 0 and 1. 0 indicating that whatever you're injecting in that specific injector actually doesn't contribute to production coming in from that specific producer. So as far as that producer is involved, that's an ineffective injector for that specific producer. Now, on the other hand, if you start getting a gain values close to 1, what it means that everything that you're injecting through that specific injector is ultimately contributing to production from that specific producer. Now, why this is important is knowing that can enable you to know, if it's a high oil producer, you immediately know if you have to take some of these injectors for maintenance, you can go back and prioritize and actually ignore the ones that are actually quite responsible for production in that respect. Of course, these models, we have turned them around. You can do it for multi-layered reservoir where you have a lot more production, commingled production, and that can help you determine how much is coming in from each layer. So these are very powerful, sophisticated techniques that one can extend, which can really help drive a lot of value, especially when it comes to optimization in mature fields, because you know how much you're injecting, how much you're producing. Once you know these Fijs, you can go back and recast these equations to perhaps ask yourself, what should be my new injection so that I can maximize my oil production. So, I mentioned about, multi-layered reservoir where you have commingled production. So what we do here is essentially you separate out multiple layers, which means you're adding more variables. Well, it doesn't matter because, you can use some sophisticated algorithms around it. And of course, you add an additional constraint that the total production that is coming out from the sum of these producers have to be constant. And of course, you can also adapt these to steam floods where, you might have, and the variation that you make is you kind of, recast those equations into a two-flow equation. and you also have a varying tau. So a lot of work, of course, has been done back in UT, and what we've done is really adapted and added multiple layers around a lot of that work. So essentially what you're looking at is this specific model, which can act as a quantitative analysis, because here you're talking about how much to inject from every injector, right? Especially when it comes for multi-layer as well as for steam floods. The other kind of reduced physics model that typically we kind of use is something called the fast march models. So the fast march models really rely on pressure diffusion equation, where you're just using the geological data as well as the fluid properties to move from a permeability map to a diffusivity map, and you can use a time of flight calculations to actually determine the drainage volumes around specific location. And I will come back to some applications of these models. They're particularly relevant in field development planning because depending on where you place the well, you can go back and use these models to compute drainage area, which can actually be inputted into machine learning algorithms, and combined with reservoir simulation, they end up making a lot more predictive models as compared to the models that you would if you were to just train machine learning model with reservoir simulation. So this is again also a quantitative approach that uses geological model as an input, as against other approaches which typically use production and injection data as input. All right, so I just wanted to introduce some of these models, some background on how some of these models are constructed, some underlying equations. So let's talk about some actual applications, and when it comes to especially mature field optimization. So in mature field, what I mean is any field which has been under water flood or gas flood for that matter. So where you have a lot more data in your system. And so when you have a lot more data that you are getting from your reservoir, some of these methods are more powerful than a traditional reservoir simulation approach. So what you can do is essentially split up into some qualitative analysis and quantitative analysis. So on the qualitative side, this is where we use analytics, machine learning, where you're trying to broadly categorize wells into groups, identifying where your thief zones are for that matter. And also the kind of questions that you answer to the qualitative analysis is knowing which of those specific injector wells are effective. On the other end of the spectrum, you can use these results and plug it back into the quantitative analysis, where there you are answering questions around how much injection is lost, but more importantly, which specific wells and how much water to inject in those specific reservoirs. Of course, we have applied these combination of qualitative and quantitative techniques to multiple fields, and I have listed out some of the fields where we've applied, and also I have referenced some of these papers which talk about these solutions. So essentially, the idea is to combine qualitative and quantitative workflows in a hybrid manner that can really help you drive solutions. And let me talk about a couple of examples around how this combination actually helps you reduce challenges associated with each individual approach. So the first challenge, of course, with some of these CRM models, when you use them as a standalone, is especially when you have large number of wells, you have too many unknowns when you're trying to solve a lot of these unconstrained minimization problems. So one way of actually determining well pairs which are not related to each other is by use of these random forest models. So the random forest model essentially helps you determine which well pairs are not related. So that way you can reduce the system of equations which you can still use then to actually go back and solve for consistent solutions. So in certain sense, the random forest model really helps you determine unconnected well pairs, and then those well pairs you can take it off your system, and you can use it to actually simplify your CRM model, which helps you, remove some false positives, as well as, really reduce and increase the solution times associated with these CRM models. One other approach in trying to combine some of these models is, trying to eliminate what we often call the false positive. Now, typically CRM models, because they assume that every single well pair are related to each other, one ends up having a lot of connectivity between well pairs which are very far off from each other. Yeah. So when you are in such a case, you really don't know, which ones to take in, which ones to neglect. So, essentially one way of trying to approach this is trying to use the fast march model, which actually tries to help you, determine which specific, essentially obtain a radius of investigation around every injector. So here in fast march model, you typically use the geological model as an input, as against the CRM model where you're just using production injection data as an input. So this geological model kind of helps you supplement, obtain the radius of investigation around every injector, which helps you determine, which are those wells which are under the purview of every injector, so that you can really eliminate a lot of these false positive. In fact, we presented this specific paper at this year's SPE conference just last month in that respect. So in certain sense, the fast march model really helps determine ROI around injector for use in these CRM models. And of course, we've also had multiple successes around some of these mature fields. So one such mature field is in Egypt, where you had peripheral injection, multi-layered reservoir. This was covered by JPT magazine in the Jan 2021 issue as an upcoming technology. So just by using cross-correlation analysis, we were able to identify how one specific layer wasn't receiving any water. And the operator, using these tools, were able to go back, drill a new injector and start observing positive results associated with them. The other value that actually we are pretty proud about is for a commingled production in California. So this is again an old mature fields, 800 wells with over 400 injectors, where each had over 27 different producing layers. So commingled production. We were able to use or recast these models to go back and say how much specific amount was coming in from each individual layer. So that helped prioritize which specific layers were getting watered out as against the other, identify which injectors to actually go back and shut. So we were able to point out and identify the effective and ineffective list of injectors. We were able to identify a list of wells to kind of reduce water recycling, and also propose new water optimization schemes that could help them just redistribute water. So you're not even looking at drilling, but just about redistributing water without any capex, that helped them cut about 20% of water and increase oil by 5 to 8%. All right. The second application that I want to talk about is around field development planning. And of course, in field development planning, something we are well aware of, it's really linear in nature, and it's been like that for a very long time, right? So you have the static model built by geologists, geophysicists, moved it over, shipped it over to the reservoir engineer who starts building a dynamic model. And of course, then you start using the dynamic model to make recovery predictions. Now, whether you are in a greenfield scenario or a brownfield scenario, in a brownfield scenario, you already have a dynamic model, you perhaps history matching it with existing field data that you have. And there is always some back and forth, right? In a greenfield scenario, what you're really curious about is the well location, the number of wells, where to place them, what controls to maintain. So you kind of vary this, and it's almost like shooting in the dark. And this is exactly the same thing that is happening now, and it was the same thing that was happening 10 to 20 years earlier. So there is a lot of manual process involved here, where you're going back and forth, you're perhaps moving the well locations around, you're running simulations, you're waiting for results. Then depending on what you get, you go back, perhaps change the number of wells, or perhaps change their location to really see if you can maximize the NPV for your given field. So we wanted to look at it from a perspective of whether machine learning could be an opportunity to actually automate and reduce the time taken to scan the entire solution space, because oftentimes you're restricted by the time period. Perhaps you have to give a solution in a couple of weeks, and that is very typical of what used to happen when I was a reservoir engineer. So that you're not quite confident that you have scanned the entire solution space of possibilities. So the idea there was, what if we could use machine learning as an opportunity to automate and reduce the time that it takes to scan the entire solution space. So just to present a comparison between the traditional approach where you're populating wells, you're running simulation, you're obtaining NPV, you're going back and forth, right? So there is a sequential approach where you're making manual changes and you're trying to wait for simulation results. And of course, it's a time-consuming exercise because you need to interact with multiple systems, setting up those simulations, especially when it comes to organizations. The servers are in Linux, these things are in Windows. So it's really a very manual process, and also even at the end of this exercise, you're not pretty confident if the well location is indeed the optimum. So, what you can do now is essentially use a single simulation file to generate multiple cases. Through that multiple cases, generate a hybrid model, which can then be used for field analysis as well as for optimization. And I shall elaborate on how some of these techniques are done. So the hybrid model results essentially are generated using very few simulation runs, and you combine them with fast match model results, and both of these are fed to a machine learning model, which helps you get more predictive hybrid models in that sense. So the inclusion of these fast match model really provides some kind of an averaging of properties in order to get these predictive models for that matter. So in certain sense, automating and use of these hybrid models can really decrease decision-making times drastically. So just to explain this a little deeper, so the way you're trying to generate these hybrid models are by combining a few simulation runs with FastMatch. So essentially you go from a single simulation file where you generate multiple simulation input files on the backend, and you're combining them, you're running those simulations, you're running those FastMatch model for each of those new configuration, and you're combining these two to generate a hybrid model, which can then be used as a predictive model for perhaps well placement scenarios, or also you can plug it with a global optimizer. So we use a particle swarm optimizer, which can help you go back and look at verifying simulations as well as predicting NPV. So just to illustrate this point, I just want to play a short video on how some of these things work. So essentially what you can do is you can go back and just zip your entire simulation file that you might have. So for the purpose of this demonstration, I'm just using the non file. So let's say that you have the entire simulation file. What I mean by simulation file is all the zip contents, including all the include folders and everything. So this is, again, we did this for an Eclipse file, but you could very well extend it to any particular simulation file that people typically use. So what it does is it first renders a browser-based rendering of your entire simulation file. So let's say that you had indicated some random locations of these 5 wells. So essentially what you then go is essentially now you can generate a hybrid model by perhaps specifying the number of simulations, or you could also essentially specify your target training and testing score. So in this specific case, you could also specify a target testing score. So I'm just putting in 400 simulations for now. So you can input some kind of a capex and opex and oil price, and some interest rate depending on what organizations have. You can run and create these hybrid models. So what it does in the backend is it generates 400 different variations of the well locations, and it generates new simulation input files, and those simulation input files are combined. It runs those simulations, right? 400 different simulations, and for each of those 400 cases, you also run these fast match model, and together they are fed into a machine learning model, which kind of helps you create these hybrid ML model that you see on your screen. And of course, these take time. I'm just showing this for a demonstration that once you have that, set it up in the evening, you come the next day. That's how a lot of our users are using. They see this entire predictive hybrid model with the well location and the NPV. Now, of course, you can move the wells around and you can know the new NPV. So you don't have to run a new simulation anymore, because this is a predictive model in that respect. So that gives you the ability to actually start placing different wells, perhaps run different scenarios by eliminating certain wells and seeing if you can essentially obtain a higher NPV. And you also know a training and the testing score associated with this, right? So if you let me just go back. So if you notice, once you have created a hybrid model, you know what the training and the testing scores are. And of course, we've run 400 simulations for a greenfield. You're possibly okay with a 70–80% testing score. So you can reduce the number of simulations that you want to run. So the higher the simulations, the better the testing scores associated with it. But you can also verify it with the actual simulation if you like. But more importantly, because there can be so many different combinations, you can plug it directly to a global optimizer. So in this case, we use a particle swarm optimizer, and that tells you, what the new locations of these wells are for a maximum NPV. So it gives you a top 5 or a top 10 case for some of these NPVs. So I just wanted to illustrate this case in point where you are going from a single simulation file to actually a decision around where could be potential locations which can help you maximize NPV. You can start and put things in a loop in some sense. So essentially start with 10 wells and find at what well number you can really get a maximum NPV. So in certain sense, you're really automating this entire field development planning process, starting with a single reservoir simulation file. All right, so just wanted to illustrate this, and we are trying to deploy this, currently deploying that for a couple of fields in Malaysia as well as the Middle East. Now, obviously, I just illustrated a case of vertical wells. You could extend something similar to even horizontal wells. So here's a comparison between the model prediction and we actually ran simulations for each of those cases. And what you notice is the prediction and the simulation data, they kind of match really well. So the secret here is, of course, the fast match model, which helps you generate these predictive maps. So this combination of simulation, reduced physics model, and being fed that into a machine learning model, that is what creates a more predictive map in that respect for your entire field reservoir. All right, so in summary, once you generate these hybrid models, what you start noticing is obviously a dramatic decision reduction, right, in your decision-making times, because you've automated the entire process, and you're also confident that you have scanned the entire solution space, right, because you know the training scores, the testing scores, so there is much more confidence in these solutions in trying to use these hybrid approaches. And as I mentioned, the real aspect is, of course, the fast match model results in the backend, which really helps you improve testing scores associated with the machine learning model. So the fast match model really kind of helps you average out, which just running reservoir simulations wouldn't, especially when it comes to making these machine learning models more predictive in nature. Of course, we have extended this approach not just to well location optimization, but also to well controls optimization, where you can really integrate this in this framework to go back and say that, once you have fixed the optimum well location, what is the pressure or, what is the drawdown that you should be maintaining in each of these wells in order to have a maximum NPV for this specific case. And of course, you can go back and say, okay, I'm doing it for a specific realization, but what if I have multiple realization? So you can go back, create multiple cases, run multiple realization, which can also be used to rank, essentially use that as a basis to go back and see, which well locations are common across multiple realizations, to go back and suggest that, that indeed should be the proposed well location for a maximum NPV. One other advantage of a lot of these global optimization algorithms, one of the challenges is currently they are typically coupled to a reservoir simulator, which means the time that it takes to really reach a global optimum, it just goes on and on, right? But if you couple a hybrid model, which is predictive in nature, directly to a global optimizer, you can run these computations much faster. You can scan the entire solution space, and it also really helps you distinguish between local and global minima, which is often always a challenge in some of these solutions. So in some sense, here's a solution which kind of integrates with existing tools, which are specific workflows. And really, what you're doing is you're moving from a single file, a data file that you had, towards a decision around, where to place those wells, how to produce them. So in some sense, driving a lot of those decisions that are relevant for field development planning, and that is what we are calling embracing this expertise in a box, because it goes back and identifies which model to combine, how to combine, which we believe is really the future of the oil and gas industry. And this is how a lot of these workflows are helping disrupt typically, the traditional linear workflow that organizations are so often used to in certain sense. All right. So I do have a few minutes. So I just want to touch upon another approach that we typically do. So this is another application where actually Adimite worked on this, where we are looking at predicting bottom hole pressure from the other data that you might have at the surface. So here typically, when you have these subsea wells, one of the challenges is while you might install these permanent downhole gauges, many times you tend to lose these gauges, and they're especially difficult to replace when it comes to subsea wells. So the question that we were pondering was, can other data be really collected at the surface? The temperature, the flow rates, the pressure that we are measuring at the surface, can that be used perhaps to predict downhole pressure gauge? So can I use machine learning as a basis to perhaps use this so that if I lose my pressure gauges, can I use them as a way to predict pressure using the other data that I'm measuring at the surface? So it turns out, one could use the LSTNet, the deep learning module, which is actually a combination of CNN model as well as RNN, the convolution neural network as well as the recurrent neural network. So the advantage of this combination, again, I would argue is that, the CNN helps identify some, short-term local dependencies, whereas the RNN helps recognize long-term patterns. So when you look at typical, bottom hole pressure data, you have both these variations, right? So this combination helps represent best of both worlds. And just wanted to show a few examples of the actual data versus the prediction. So what we've done is we've used the Valve field case as an example. The blue line represents the actual data. So what you notice is there is local variation as well as long-term variations through these pulses. And this prediction is coming from the LSTNet, where we are using temperature as an input. So essentially the temperature that we are measuring at the surface, and what you notice is some improvements obviously from what has been proposed. So again, the whole idea behind this is, could we use essentially the surface data that we are collecting to predict what's going on at the downhole? So what you notice is, by using qualitative rates that you're measuring at the surface, you can still predict some of these bottom hole pressures. But what we observe is a combination of different inputs, whether it comes to time interval, temperature, gas, typically tends to give you some really good results when it comes to a lot of these bottom hole pressure prediction. So we are actually deploying it to predict bottom hole pressures. Of course, these modules can be integrated with GPUs. We're using GPUs for the learning part of it, and of course, they themselves can be combined with other analytical approaches. So that's the hybrid model that I was talking about. So we're using LSTNet approach along with a hybrid model that has been developed, and trying to deploy that as a dynamic workflow for a field in Australia, where you have a continuous input, continuous learning. Essentially, you're getting data from the field so that you are prepared in the eventuality that some of your bottom hole pressure can actually and fail, and hence you're really trying to avoid this costly well intervention, which can be pretty significant when it comes to subsea wells. All right. So, of course, the devil is in the details. So, our expertise in a lot of numerical tools really help us allow embracing these hybrid approaches. I spoke about nonlinear optimization. So what we've really done is adapted some of the advances in optimal control theory to make sure, some of these unconstrained optimization problems can give you consistent solutions. And of course, we use typically penalty functions that help us convert from constraint to unconstrained problems. So obviously that throws open a lot more ways then to try to solve them. We've also adapted from some useful package. So not directly using them, but trying to see how some of these packages can be adapted within our framework of problems that we solve to try and make sure that we get consistent solutions. So one such example is, so one of the challenges in unconstrained optimization is typically because you don't know whether you will get a global minima or a local minima. So what we do is we use results coming in from the qualitative analysis, feed that as an input to the quantitative analysis. So that helps really get consistent solutions. And the other innovation that we've done really is, try to use GPUs, which can help really speed up a lot of solutions when it comes to 500, 600 wells that you're talking about. So essentially use or construct some of these problems in a TensorFlow framework that can help really drive a much faster decision-making times associated with some of these hybrid models. All right, I just want to leave with this thought of how we are really at an important cusp in the industry. So if you reflect back, the 60s and the 70s, where simulation was being popular, and of course, I'm sure there would have been some resistance back then to use these models. But when you look around, in the last 30, 40 years, obviously they're much more pervasive, right? I mean, that's become an integral part of decision making over so many different years now. And what I would like to argue is the 2020s are going to be the hybrid model, the world of the hybrid model, where you will be using a combination of different models. So not necessarily just simulation, but perhaps some other data-driven models, some machine learning approaches. You will be combining them, of course, in intelligent manner. And the trick would be, or the challenge there would be, to know which particular data to use for training. So that's where a lot of domain expertise is going to play an important role. And of course, a lot of this is also going to come and reflect in automation, because it's this automation which will really drastically cut a lot of these decision-making times. So in certain sense, we believe that hybrid models in the backend will drastically reduce decision-making times, and they will really be ushering a new era of reservoir engineering expertise in a box solution. So whether it is, just using your data to know, which specific wells to inject, how to inject, right? So you're going from data to decisions, or just using a single simulation file to go directly to knowing where to place your wells and what rates to produce them, or the other application that I spoke about, where just using the surface data that you're measuring to go back and saying, if my bottom hole pressure gauges fail, what is the specific how I can predict that using the deep learning module, or a combination of that deep learning module with a physics-based model that we have. All right, I just want to thank the SPE-Austin community for giving me an opportunity, and we are always grateful to our user community and our early users for embracing some of our innovative approaches. Of course, there is only so much I can do myself. We are really proud to have put together a team from industry and academia, folks who have at least 2 of the 3 skills that I have listed. My background, of course, as I mentioned, as Adimite mentioned in the introduction, a lot of my academic contributions have been in the improved recovery space, and I've done a couple of postdocs around high fidelity algorithms, looking at how GPUs can essentially speed up compositional simulations, a lot of physics-based approach. So we come to these hybrid models from a domain standpoint, and how some of these algorithms can really drive decision making on the domain side. And these are also a list of recognitions. Of course, the most promising startup award at Offshore Technology Conference gave us a start, and we are very pleased to also inform that the inaugural technical award in data science and engineering analytics was a good testament to some of these hybrid models, and to see how the industry is really embracing some of these models. So in certain sense, we are working with different oil and gas companies, where we are obviously moving from data to decisions by also integrating with a lot of the digital transformation projects, because a lot of these projects tend to concentrate more on the data side. So essentially, how do you use those data to actually go back and create these unique workflows, which can really drive decision making around injection operations, or even field development plan in that respect. These are some of the publications that I referred to. Our specific publication, of course, in the slides I refer to a lot more publications, and they showcase some of our successful deployments for mature fields. So yeah, I think this is what I wanted to share. We are really driving hybrid models for reservoir surveillance and management. And that's the central message that I wanted to pass, that, hybrid models are the future. So thanks for the opportunity, and happy to take any questions.
Okay, thank you so much for the presentation, Ashwin. So I'm gonna read out questions to you, so you have an idea of what people are saying. There's like a lot of questions. So sorry about this. I'm trying to navigate the Zoom space so I could share my screen back again. Okay, so basically, so far we have questions, Ashwin, starting with Tim's question on how accurate are the predictions? Do you have any field data proof? If there are any inaccuracies in the model, how do you use the tool to determine the physical assumptions made to the simulation model were inaccurate? For example, infill well placements and interaction with hydraulic and natural fractures. So how do you respond to that, Ashwin?
So I presume this is related to the greenfield, brownfield space that I spoke about, the application that I spoke about. So, essentially what you're looking at is the accuracy of the prediction. I think we compared what the hybrid model predicts versus what the actual reservoir simulation predicts, right? So, that kind of accuracy we kind of established, which is also reflected in the testing scores that you point out. So if you look at one of my slides where I spoke about, ML results versus the actual simulation model, you notice they lie around the X equal to Y line. So that was one aspect. And of course, that's purely numerical accuracy prediction, if you will, right? The field data proof, of course, these are field development plans. So how would you normally do any field development plan, right? You still use a reservoir simulation model to try and come up with a field development plan, right? And the time lag between, going from a field development plan to an actual drilling is obviously longer. So we'll have to wait for some of these field data proofs. Although in several of these brownfield cases, what we've observed is, and we've done some of these comparisons where, you can use essentially, and I can draw from one experience around water injection. So, you can go back and look at, where the specific injector is pointing towards. So let's say you're trying to place an injector, you're doing this hybrid model, it's pointing towards one specific location where you might want to place it. You can go back and actually look at the saturation map and go back and, do some consistency checks on whether that indeed makes sense in that respect. So those are, some of the ways in which you make consistency checks. But, what I really want to draw here is you're still using the same tool, but you're using it a little more effectively in trying to determine whether it's well location or, for that matter, essentially the field development plan through that.
Okay, so the next question we have is asking you to elaborate on how the test scores were calculated.
So, I think the test scores, I think that would take a little longer to explain. I can reach out to the person again and we can go for it.
Okay, so I'll put that on hold. I could help facilitate that. So we have a question from Alberto asking what criteria you use to place the horizontal wells in the model, like the tubes, direction, length.
That's a good question. So one of the challenges is, do you fix? So we've done both. So what we've done is we fix the length of the well and move that around. We've also added another layer of complexity where you say not just the length is fixed, you could also vary the direction of the well. So essentially we've done it both, but we do it one after the other. That helps kind of in the computations overall.
Okay, so the next question is on the LSN work. It says, could you clarify if the results are on the training data or prediction or testing data, the results you presented? And also, what was the time window used for the training and prediction?
So typical, I think I would say that, if we have 3 years of data, we use 2 years, we split it between 70-30 or 85-15, right? Adimite, I think you were the one who did that work.
Yeah.
That's the kind of split that we often do. And obviously it's critical that the testing data is something that makes sense, right? So we've done a few blind tests to actually notice whether those kind of make sense in getting that, right? Do you want to add anything, Adimite, on that?
So basically what we did was we created a training data set using the 70-30 approach, as Ashwin said, but out of the 30, we still kept out some for validation, and we also tried validation on the new different data set that we had for that particular field. As to regards the time window, so it's dependent on how much we want to see, but I found out that the least window we could use to get efficient results was actually a 14-day window, which is like 2 weeks, which I feel is reasonable enough to be able to get predictions for the pressure in the next step. So I hope that answers your question, Sanjeev. I'll be more than welcome to tackle that in breakout rooms and have in the next session. Ashwin, you do have another question from Ricardo asking, what do you think of using pins for reservoir simulation in comparison to hybrid model? Ricardo, do you want to unmute yourself and clarify your question?
So what is pins?
Yeah, I was just asking him to clarify his question.
Yeah, it's physics and neural networks.
Oh, okay. I don't have an opinion because I haven't used it. So I can talk about what we have done. What we have noticed is you can't just run a bunch of simulations and feed it to a machine learning model and wishfully think that you'll get a predictive model coming out of it. So that doesn't work. And what we have observed, what works is combining that with a reduced order model in a hybrid approach and putting that to a machine learning model kind of works. Now that machine learning model itself could be a neural network model, it could be a gradient booster algorithm, what have you. And amongst those, what we have observed is that the gradient booster algorithm typically works well.
Thank you.
Okay, so the next question is from Claude. He's asking if this is the present state or more of the future state of reservoir engineering workflows. What's the most critical thing we need to look for in the future?
I think that's a great question. Actually, unfortunately, the present state is still this manual back and forth. Think of the earlier thing I started, right? A guy trying to book for a hotel in New York, going through the yellow pages and stuff. That's the state right now, right? Right now, we have all these models lying here and there. You don't have an integrated approach towards decision making. They exist between different teams. Of course, you've heard that a lot more, right? Data is in silos and so on and so forth. But I think what we need to focus on as a community is to look at quick wins around automation. So are there simpler things that we could do which can automate the process, reduce the decision-making time? And this is of utmost priority, because if you look at the global workforce, we're going to have a much smaller workflows. And the only way we are going to meet the world's energy demand is by driving quick decision-making, a lot of automation in that space where you're not just relying on a single approach, but using a combination of approach, given that you have access to that data, to use these combination to really drive decision making. So to me, that's critical. The automation part is what is critical as we look towards the future.
Okay, so we have another question from Sanjeev asking if you could talk about the challenges with hybrid model, for instance, balancing the physical model simulations and hyperparameter tuning, or integrating your data, tracking data lineage, etc., things like that.
Well, I think, we didn't see a lot of challenges in that in terms of hyperparameter tuning. What we observe is that your testing scores vary with the number of simulation runs that you do. And of course, I'm saying that in the context of integrating it with fast match model. So when you use these two combination, what you observe is as you increase the number of simulations, your testing scores also increase, which is actually a good thing, which means you can set a target for your testing score, because typically companies operate where you are okay having 70% or 80% accuracy. I would say 70% accuracy on a greenfield simulation, right? That's an accepted accuracy. So which means you don't have to run 400 simulations like I showed, where you got an accuracy of 95%. You can still run something in the tune of I would say 50 simulation runs that can leave you in the ballpark of 70 or 75. And mind you, the non-field itself is a highly heterogeneous field, if you will, right? So it's not like you're just running these cases for a homogeneous reservoir and magically getting all these testing and training scores. This is a highly heterogeneous field, which is where the central idea of coupling it with a reduced physics model comes in if you're trying to create a lot more predictive machine learning models.
Okay, so does anyone else have any questions before we proceed? Okay, so I would say I could ask my question now. So Ashwin, you showed us an example on non-field, which is a brown matured field. Have you deployed any of this on green fields?
Oh. Yeah, when we ran this, the case that I showed was just taking the geology of non-field and imagining that you were doing a field development plan for the non-field. So it just assumes a particular oil saturation distribution, if you will. So the approach is, let me take the geology, let me take the properties and think of it as a green field and essentially see how it behaves. Yeah. So now what we've observed, we've been doing some projects where you could do this for conventional reservoirs, for unconventional reservoirs, for gas fields, for oil fields. So essentially, because in each of these cases, you're still relying on reservoir simulation as your primary decision-making tool, right? So as long as you're using that, this hybrid approach can really drive faster decision-making in that respect.
Okay. So thank you so much for your time, Ashwin, and the presentation. It was quite informative. So now we're diving into the networking part of the event. So basically, to foster engagement, there'll be 3 breakout rooms created by GL. The first room will be talking about integrating physical conditions into machine learning models. The second room is on how to translate model results to business cases. And the third room, it talks about what are the current risks and concerns with applied machine learning. Just to be sure, just to let you all know, nothing is set in stone. These topics are just provided to help foster discussions. However, feel free to discuss anything that feels most relevant to you, or you could even as well just, socialize. Anything is literally welcome. The breakout rooms, I'll be moderating breakout room 3. Anna will be moderating breakout room 2. Christopher will be in breakout room 1. And Jill will be setting us up now in our breakout rooms. So looking forward to seeing you there. It may take a bit of 2 minutes or so, 3, to get us started on the breakout room session. So yeah, thank you. Ashwin, you're more than welcome to join any of the breakout rooms to,
Sure.
Join the conversation. Yeah. Oh yeah, sure. So someone asked me to show the topic again for the breakout room. So topic 1 and breakout 1 is integrating physical conditions into machine learning models. Topic 2, that's breakout room 2, has to do with how to translate model results to business cases. Breakout room 3 deals with what are the current risks and concerns with applied machine learning. As I said, this could change. Nothing is actually set in stone. So yeah.